For decades, the hunt for extraterrestrial life relied on patience. We pointed massive dishes at the sky, listening to the static, waiting for a deliberate radio broadcast from the dark. The math laid out in the 1961 Drake equation framed the problem. The universe contains trillions of galaxies and billions of suns. We were searching for a needle in a haystack, so impossibly large that it overwhelmed our best instruments. The irony is that space isn't empty. Organic molecules, the carbon-based building blocks of biology, are scattered almost everywhere we look, from distant dust clouds to passing comets. But finding these molecules on a rock does not prove the existence of alien biology. Ordinary, non-living chemical reactions can easily forge these exact same structures, creating false positives that lead nowhere. Astrobiology had hit a wall. To find actual life, researchers realized they had to stop casting a wide net and start treating the universe like a crime scene, applying strict, targeted forensic science. That meant abandoning the broad sweep of the cosmos. Astronomers threw out the billions of random stars and began isolating a highly specific suspect list. Recently, they filtered thousands of known exoplanets down to exactly 45 rocky worlds. These targets sit squarely in their star's habitable zone, where temperatures are right for liquid water to pool on the surface. We are also investigating crime scenes much closer to home. Right next door on Mars, the dried-up ancient riverbed of Jezero Crater offers an accessible physical testing ground. The Perseverance rover drilled into a rock sample there dubbed Sapphire Canyon and detected specific minerals, including vivianite and greigite. On Earth, these specific minerals are routinely left behind as waste products by microscopic organisms in swamps. But biology and geology can look identical at a glance. Confirming that these are actual biological traces requires an entirely new method of chemical fingerprinting. For targets outside our solar system, we use the James Webb Space Telescope. It operates as a forensic tool designed to interrogate the atmospheres of those 45 distant suspects. A team led by Dr. Niku Matasusan pointed the telescope at K2-18b, a massive ocean-covered world 120 light-years away. Inside its atmosphere, the telescope detected two specific molecules, DMS and DADS. Here on Earth, these chemical structures are produced exclusively by living organisms, like marine algae. Even with complex molecules, a lingering doubt remains. Could a dead planet manufacture them by accident? Researchers at UC Riverside found a way to answer that using statistics. This chart maps the distribution of amino acids produced by dead, abiotic chemistry. Non-living processes scatter materials in a chaotic, uneven pattern. But biology operates differently. Living systems reorganize these molecules into highly varied but remarkably even and structured statistical distributions. Life organizes chemistry. That mathematical pattern is a universal fingerprint, allowing us to separate living ecosystems from dead rocks, regardless of what the alien biology physically looks like. Movies train us to expect a sudden, dramatic moment of contact, a saucer landing on a lawn, or a clean audio signal cutting through the static. The scientific reality is far more methodical. Discovering life will be a gradual, undeniable convergence of these distinct forensic data points accumulating over time. The tools are finally in place. We have the physical coordinates on a 45-planet shortlist, the optical power of the James Webb Telescope, and the mathematical models to read the chemical fingerprints. The noise of 1 trillion galaxies has been filtered out, and our instruments are locked onto targets with the highest probability of success. We are no longer passively scanning the dark, hoping someone waves back. We are actively dusting the cosmos for fingerprints, and for the first time, we know exactly what to look for.